Hello and welcome to my continued quest to try to keep my brain fresh as I get older. Um, I'm on the third section of James Stewart's sixth chapter on calculus. This is the third section on volumes by cylinders. The previous video was on volumes by washers. But anyway, let's refresh ourselves, shall we? So what we've been doing, and this is pretty standard for high school calculus, somewhere on the calculus AP, AB calculus exam, there will be some sort of an area or volume issue like this on the SAT calculus. And so what we do in these sorts of problems is you take some graph like this, y equals x minus x squared, and you rotate it around something. Now, I'm going to go easy on myself and rotate this around the y-axis, that is around x equals 0. So we're going to rotate it, and it's a bad drawing, but you get the sense. We've taken this underlying x minus x squared, and we've rotated around x equals 0. And we've got this strange shape here, mold, I don't know what you want to call it. But let's say we want to find the area of this thing that has resulted. By rotating this, you can see here's the mirror image of it on the other side, and where we've rotated it around. How do you find the area of it? Well, in the previous section, we used a washer method. So in the washer method, how would you do it? Do little slivers, but there are certain places where using a cylinder method is just a whole lot easier. So you can think of this as being a bunch of up and down cylinders, from small ones to bigger to bigger, 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 and so you've got inside of this, whatever the shape is, you have an infinite number of little cylinders, where delta x is kind of like the thickness of each slice. That's what we're going to take the limit as it approaches 0, as it were. This is going to become dx. When we go into integration. And what is the volume of a cylinder like this going to be? Well, it's very easy. The volume of a cylinder is the area of the base, times the height. Well, the area of the base is going to be 2 pi r, whatever the radius is. In this particular case, the radius is just going to be x. And then the height is y, right? So the height is x minus x squared in here, because that's what the y is, and so that's the height. And then you've got the thickness that brings in the three-dimensional aspect to it. So it's not just an empty cylinder. There's a thickness to it. So basically, here's the formula: the volume of each individual cylinder is going to be the circumference of that cylinder times the height of that cylinder times the thickness of that cylinder. So in this case, we've taken, this is the circumference, 2 pi r. Which ends up being 2 pi x, because remember, x is the radius, and then the height, which is y, and then the delta x. And so if you substitute x minus x squared for y, ta-da, we got a little formula to work with. Okay, so here's the general concept for this volume by cylinders. What we're going to do is we're going to take an infinite number of slices of cylinder, and the smaller each slice gets, that is, the smaller delta x gets, the more accurate the volume that we arrive at is going to be. So we're going to take infinite slices. So from I equals 1 to infinity, the limit as n approaches infinity of the sum of all the slices of 2 pi x, which is the circumference of every little cylinder slice, and then y is the height of every cylinder slice, which remember was x minus x squared times delta x. And if we another way to put this, of course, in integral language, is the volume from a to b of this bit here. F of x is just another way of saying y, and then dx means we've gone infinite. Now, what is the a to b? Well, you're going to have to kind of discern it in every circumstance. So, like in this case, here's what I did for the a to b. I asked myself, where does x equal 0? Because that's what I'm going to do. We're going to take the sum from x equals 0, pretty obvious, to here. But where is here? How do I know what the b is? Well, basically I solved for where does y equal 0? Well, y equals 0, if I factor this, I get x times 1 minus x. So when x equals 0, y is going to equal 0. And when 1 minus x equals 0, y is going to equal 0. Well, 1 minus x equals y, solve around, or 1 minus x equals 0, solve, and we have x equals 1. And so what we ended up doing is going from 0 to 1, inferring it from the situation. And I plugged in the details here. So 2 pi x is the circumference of each cylinder slice, because remember, the radius is going to be the x. And then this is the f of x, or the y, x minus x squared, and there's my infinitesimal slice. And so let's go ahead and do a little solving. Now, I somehow made up this problem on my own. It's not exactly like any of the problems in Stewart. So let's pray that I did my math right, because like I said, my brain's getting old. I think I did it right. So basically, we multiply this out. You can always take a constant outside of the integral thing, so that 2 pi comes out, very regular. So we have x times this, so that's x squared minus x cubed. Yeah, we're good so far. Okay, so now we're going to integrate this thing. Okay, so the 2 pi we already have out, so we're going to integrate each one individually. There should be a minus sign here, which means I've already messed up. Let me pause the tape. And voila, it's fixed. Okay, so this should be a minus here. So what we do is we integrate x squared, which is x cubed over 3. We can check ourselves by differentiating it. So if you take the derivative of this, 3 times 1/3 cancels out, and you're left with x squared. Ta-da! And same thing here, x4 over 4. If you multiply 4 by 1/4, it cancels out, and you're left with x cubed. And so this seems to be the correct integral. And so if we do b minus a, first we plug in the 1 here, and you have 2 pi times 1/3 minus 1/4, which ends up being 1/12. And you subtract that by plugging in the 0, which is 0 minus 0 equals 0. So we're left, basically the b minus a, the a cancels out because it ends up being 0. And so I'm left with this is what this is. And so the 2 and the 12 cancel out to 1/6, and we're left with an answer of pi over 6. So that's basically how you solve in instances where it's better to make a cylinder out of it than a washer. And it worked very nicely in the problem that we have here. So our next video is on using these principles to figure out how to work the value of work. And we'll do that next.